Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Okay, let's dive into one of the most fundamental areas of mechanical engineering, understanding how fluids move, how they behave, and how they transfer energy. We're going to build our conceptual toolkit step by step, starting with the absolute basics and then moving up to the powerful principles that engineers use every single day.
All right, so first things first. Before we can even think about controlling or analyzing anything, we've got to be crystal clear on what it is we're actually working with.
So what's the real difference between a solid and a fluid? Well, it all comes down to how they handle force. See, if you push on a solid, it might bend a little, but it generally holds its shape. But apply that same force, what we engineers call a shear stress, to a fluid, and it just gets out of the way. It flows. That continuous movement is the key.
Now, fluid is a pretty big category, and it covers both liquids and gases. And while they both flow, their differences are absolutely critical. Liquids, they're tough to compress, and they'll only fill a container from the bottom up. Gases, on the other hand, super easy to squeeze, and they'll expand to fill every last nook and cranny of whatever space you put them in. This one difference means we have to use totally different approaches to engineer them.
To really understand a fluid, you got to know its stats. These are the properties that control everything it does. You've got density, which is its mass per volume. Then there's viscosity. That's just its resistance to flow. Think honey versus water. These properties are the very first tools we reach for when we start to analyze any fluid system.
Okay, so we know what a fluid is and what its key properties are. Now let's check out the rules that govern it when it's just sitting still.
This might sound kind of basic, right? Fluids not moving. But this is the principle behind some serious, heavy-duty engineering. From massive dams holding back entire lakes to the hydraulic lift that picks up your car at the mechanic. And when a fluid is static, the single most important thing we're thinking about is pressure.
Yeah, that sounds super technical, but it's really just a formal way of describing something you've totally felt before. You dive into a swimming pool, and the deeper you go, the more pressure you feel in your ears, right? Well, this principle just says that at any one depth, the pressure is the same everywhere. It's a fundamental rule for any fluid just hanging out. Okay, static fluids are one thing. But let's be honest, things get way more interesting and a lot more complex when we put them in motion.
So to analyze a moving fluid, engineers have two basic ways of looking at the problem. We could try to follow a single tiny particle of water on its wild journey, that's the Lagrangian method, or we could just pick a fixed spot in space and measure everything that flows past it. That's the Eulerian method. And for most real-world jobs, like designing a pipe or an airplane wing, that second approach is way more practical. To help us see what's going on, we use a few key concepts. A streamline is like taking a snapshot. It shows the direction of the fluid everywhere, but just for one instant. A pathline, though, that's the actual trip a single particle takes over time. These are the tools that help us map out and make sense of the invisible dance of a moving fluid.
Theory is awesome, but to actually apply any of this, we need good, reliable ways to measure what's happening in a real system. And the story of how we first started doing that is pretty cool.
Okay, picture this. It's the 1700s, and an engineer named Henri Pitot is standing there, watching the river scene flow past. And all of a sudden, he has this moment of pure engineering inspiration. He realizes that he can use the river's own force, its own kinetic energy, to measure its speed. So what does he do? He grabs a simple glass tube, puts a bend in the end, and literally runs back to the river to test out his brilliant, incredibly simple idea. And what's truly amazing about this story is that this elegant concept is still a cornerstone of modern engineering. The Pitot tubes that measure the airspeed on a supersonic jet, they work on the exact same principle as that first glass tube Henri Pitot dipped into the Seine all those centuries ago. Of course, since then, we've built on that foundation in some pretty incredible ways. Today, we use everything from tiny turbines that spin in the flow to powerful magnetic fields that can measure the velocity of conductive fluids without ever even touching them. All right, time to add another really powerful tool to our kit. We need the ability to account for all the energy in a flowing system. This is where fluid mechanics shakes hands with thermodynamics. The first thing we have to do is define our system boundary. We draw this imaginary box, called a control volume, around the part of the system we care about. We're not trying to analyze the whole river, just what happens to the fluid between the inlet, point 1, and the outlet, point 2. Now, don't let all the symbols in this equation intimidate you. This is the steady flow energy equation, and it's basically just a very detailed energy budget. All it's saying is that any energy you put into the system, whether as heat or work, has to be balanced by the energy that comes out. Energy is never lost, it just changes form. It's the first law of thermodynamics in action. And in a lot of common situations like air flowing over a wing, we can boil that big, complicated energy equation down to this little beauty, Bernoulli's equation. It shows us a critical trade-off. Wherever a fluid speed is high, its pressure is low. And where the speed is low, the pressure is high. This single idea is what generates the lift on an airplane, and it's even what makes a baseball curve.
Okay, so we've defined fluids, we've analyzed them at rest and in motion, and we figured out how to track their energy. The final tool in our basic kit is the power of prediction. You can think of any fluid flow as a kind of tug of war between different forces. You've got inertial forces trying to keep the fluid moving, viscous forces acting like friction to slow it down, and of course gravity pulling on it. The way the fluid behaves depends entirely on which one of these forces wins the battle.
Now here's the thing. We can't always build a full-size jumbo jet or a massive dam just for testing. It's not practical. But the law of similarity gives us an incredible shortcut. It says we don't have to. We can use smaller, scaled models in wind tunnels or water tanks and still get incredibly accurate results, as long as we make sure the ratios of the important forces are the same in our model as they are in the real thing.
And this is the final, powerful idea that ties it all together. This one principle gives engineers the power to design and predict the performance of everything from tiny microfluidic devices that fit on your fingertip to massive turbines and supertankers, all by understanding and replicating these fundamental relationships between forces. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.